In what?
That we forgot to vote, they mentioned it.
In the group chat, that group, what is it, group
Does this
meeting?
mean just our votes are counted because we're shut up or not?
No, you can't, you gotta be fair about this. So here's what I would like to do. On Wednesday, would you remind me, and would everybody remind me to ask for when you want your first test, and we'll just put the votes, we'll put down some dates and vote on it, okay?
What days do you have in mind?
Any. Doesn't, see, I'm the it doesn't matter to me. It matters to you because you got other stuff going on. I come here every day of the week. I mean,
is there like a certain like range where it's like where it should be?
okay, here's what I normally tell people. If they're gonna ask me a straight question, I tell people it's better to do it after the chapter 3 when we do electrostatics. So don't do it like right now. You just got transmission lines. Wait till you get electrostatics, at least maybe a little magnetostatics. So it's going to be another couple of weeks, probably 2 or 3 weeks, okay? And then select. But if you don't want to vote now, we don't have to vote now. We can vote if we want to vote. But this is totally the ball's in more or less in your court. And the reason I do this is every time I set a date, somebody will have some unbelievable burden. I've got 8 tests that day. They'll have some grandparents die. It's always like this. But if you vote, I can't. Just go argue with the class. I'm out of the loop. All right, you follow me on this? Let's do the bounce diagram stuff. We were on that, right? You know, some people were looking at, I don't think people really got the whole gist. Didn't I put some homework up about bounce?
You had one problem on it. You put one problem that we had already done before, then that problem, and then a problem about proving something. Proving the voltage and current with the capacitor intersection.
Oh, I don't. All right, so here's what I want to do. I want to do, you got the basic idea of how to do a bounce diagram. You're just tracking how far the wave has ricocheted, you might say, at a given length of time, then adding up all the components, right?
Yep.
I'm going to go through this. So why don't we start doing, it's been one of the days, it hasn't worked out. I didn't eat anything today. I did have a little, this pre-workout stuff. And ran back here, and like one of the things, trying to work out at lunch like so many of the other friends I have. But this time I did a budget break for time. Oh my gosh. Great book here. All right, so you do though. Whose book is that? It's yours. Why don't we do in the bounce diagram, the first problem I think I assigned, didn't I?
Wait, what?
You assigned
you assigned 4. Or what? Yeah.
42, 44, and 47, but 42.
We did 42. Let's go to the next
Did you
one.
assign 4-3 or 4-4?
2, 4, 7.
Okay.
It's 242, 244.
All right, what is 43? We did 42, you said, right?
Yes.
Yeah, we
All
did
right,
2.
what's 43?
There's a figure 2.35. I have no idea where that is.
Let's take a look.
I don't know where 235 is. This really goes. 235.
One more.
2, 3.
No, that's transients, yeah.
This guy.
Okay, I got it. All right, hold on. Let me just draw that. We're gonna bang these out. This is 2-43, right, or 2.43. And here we've got a voltage source, right?
Yep.
And then we got a source resistance, probably. I think he calls it ZS, though.
It's RS.
Okay, RS. And then we got a switch that closes, I hope at T equals 0.
Yep.
But it doesn't have to. And this comes down here, and we got a load. I'm just going to call it ZL here. These are strict real in this case. Switch closes at T equals 0. Length of line is what?
10 centimeters.
10 centimeters. And the velocity on the line is?
2/3 the speed of light.
All right, 2/3 of C. What is ZL?
Is
150 ohms.
yeah.
150 ohms. And what's the Z naught on this thing?
50 ohms.
What is it?
50 ohms.
50? That's, by the way, typical impedance for any kind of microwave measuring equipment in typical microwave designs that are on chips and boards. However, any of the cable, like Spectrum, all that stuff, Cox cable, that's 75 ohm coax cable. Make sure you remember that kind of stuff. Always look at the characteristic impedance of the line, or else if you go from 50 to like 75, then you're gonna get a bounce right at that transition. What else? What's RS?
30 ohms,
30 ohms, and what is the voltage?
10 volts.
10 volts. Okay, and what do they want?
They want, for 2.43, they plot out the 2 nanoseconds, the voltage at the source end, at the middle, and at the load at the end of the T-line.
Let's do the load first, then we'll go in the middle, and then at the source, you say?
Yes.
Okay. So the way I generally speaking get these, first thing, it doesn't matter the order. Usually I get the length of time it takes for the wave to go from one end to the other. So this is, I think Whitworth's book calls it TL, it's just the time it takes for the wave, from the time you shut that thing for that electromagnetic power or electromagnetic signature to move down and hit this. And that's the length of the line divided by the velocity. The length is 10 centimeters, right? That's 10 to the minus 1 meters. And this is 2/3 of C, and C is 3 times 10 to the 8 meters per second. So this is going to be equal to 1/2, right, times 10 to the minus 9th, it looks like. Unless I'm doing this wrong. And that is going to be equal to 0.5 nanoseconds. Correct, class? Again, I'm just calculating the delay time. Y'all agree with this? I put the solutions up to these things so we can check them as we go. And if you can get them up on your laptop, it's great. Yeah, but if not, that's okay. All right, y'all agree with this? People?
You.
And you can get your calculators out if you want. So next thing, we got to calculate reflection coefficient at the load and reflection coefficient at the source. At the load, it's always the impedance you're going into, or it's 150 minus the impedance you came from, or 50, over the sum of the two, or 200. And then at the source, it's the impedance you're going into. This looks like a Thevenin equivalent circuit. So it's 30 minus 50 over the sum, or 80. For this one, we got what? I got 100 over 200, or 1/2. And for this one, I've got minus 20 over 80, or minus 1/4. Do you all agree with this? Yep. Again, just going through the motions, correct? Any questions on what I've done so far? Okay? All right, next after that, what we're going to do is find the voltage right here that I call V prime, and I think it's consistent with his book. That's the voltage that's going to occur just after the switch is closed. All with everybody? All right, so we use the 50 ohms here. We don't use the load impedance. So here, my V prime is going to be the source voltage, which is 10, over Z naught, right? Over Z naught plus RS. So that's going to be 10 times 50 over 50 plus 30, or 80, right? So that's what? 5/8 of 10, so blah, blah, blah. 6.25 volts, right? You all agree with that? Just checking on this.
Are you just doing like a voltage divider to get
So, yeah, this, remember, when the switch closes, we want to calculate the voltage on here.
Yeah.
Now, it doesn't know what's downline. There's no time. At that instant,
Just the
it looks
one.
like Z naught, and then to get this voltage, it's just the voltage division. Z naught times Z naught over RS plus the voltage driving it, source. Does everybody follow me on that part?
6.25.
Did you get that? If I'm right.
No, well, I got that. I did not get. I mean, if that's 6.25, then yeah, I got that.
Okay, well, I mean, y'all agree that there's nothing wrong on the board yet, is there?
Nope.
I'm not trying to get it wrong here. Okay, so that's it. Now, we're going to go ahead and do the bounce diagram over here. And this is only thing you're doing. You don't care where the voltage is taken. You need this. So what I'm going to do is come down here, come over here. Here's the load, and I have to put these marks that are just time constant. Time it takes to get down the line. I don't know how many they want. I'm going to go down to here. So this is going to be, here's 0. here's TL, here's 2 TL, and TL is a half a nanosecond, 3 TL, 4 TL, and 5 TL. Everybody with me on how I...
Wait, TL is what? Is it half a nanosecond?
See this?
TL is just there. Okay.
That's
it wants
the time
it out
it
to.
takes.
It wants it out to 2 nanoseconds.
That's
Then.
all right. That's only, what, 4 of them?
Yes. Yeah.
All right, so now we're gonna do the old bounce,
Yeah.
if it works. And I'm gonna go ahead and start here at 0. Now, the only thing I'm doing is drawing lines. I'm not putting any values now, I'm just showing you. If you have engineering paper, this is probably a joke. So this is the direction of propagation. Now, I'm gonna put the values on. Everybody follow me? How come I did what I did? I just cross that on to the next page. I don't mess around erasing. I'm too old for that.
I just moved it a lot.
Okay. But you all follow me why I did this? I'm just drawing lines that is ultimately the signal's propagation of the electric, really it's the electric field or voltage propagating, it's hitting here, here, and here, and here. This is the time, and this is the position along the line. You might say it's Z. And this is the load, and this is the source. Y'all with me, class? Okay, now, please listen. Next thing I do, before I do any calculations of actual voltage at points, I go ahead and I say, I know this one, just as the switch is closed, is here, is just V prime. Y'all follow me? Now, if I wanted to know the voltage, say at the center of the line, I draw a line right through here, and it's 0 here, and until this V prime crosses that point, it's still 0. When it crosses the point, it becomes V prime. Do y'all follow me on that, class? Now, I'm going to draw this down here. This is V prime. This waveform coming this way is going to be V prime times the reflection coefficient of the load. Remember, you got load and you got source. And it doesn't matter what they are at this point. Y'all get me on this? I wish I... Next, what's going to happen here? This is an incoming voltage. It's here. What happens to the reflected voltage? It's V prime gamma L, right? Times gamma source, because there's a source reflection coefficient. Y'all with me? I think you get an idea what's going on. What do you think happens here?
Multiply that over gamma L.
Right, now this becomes V prime gamma source gamma L squared, right? Down here,
Another square source.
right now it's V prime gamma S squared gamma L, and let's see, that's 2, right? Is that 2?
Well, one gamma L squared B squared 2.
Yeah, it is. It's because your professor is not being very kind. But you all follow it. Actually, that doesn't matter on that. It's after 2 nanoseconds.
Yeah, it only wants up to.
But
Yeah,
it should be squared.
Yeah.
All right, everybody with me?
Yeah.
Now, next, you can put the values in if you want, but you don't have to do anything yet. So let's get the voltage first at the load, then at the middle, and then at the source. If you want to, we can do the middle first. That's the easiest. Let's do the middle first. And I'm going to erase this and do it over here. I bet you guys see this in hard. I'll use different colored markers, and you'll see this.
So the reason why we want to match is because so this doesn't happen.
That's right. That's
This is
exactly.
really bad.
Because what happens is when this reflection coefficient is 0, nothing reflects back.
Yeah.
Yes, that's what we're always after. But you have to understand bounce diagrams because this happens a lot too. When you've got weird things happening in circuits, let me just give you a macroscopic example. I've got cabling running through there. Somehow it ain't working. So wherever the impedance discontinuity is, whether it's a short or an open, something out there happened. The line could be sheared, could be pinched off. Do y'all follow me? Just a coax cable running through. So how do I figure out about where that is? I don't want to dig up the whole wall. So what I can do is, if this coax ran behind the wall, if I can come here and I can use what's called a time domain reflectometer. All right, we can do it ourselves. You can actually get it's twin trace scope. You trace it, you turn the circuit on or push a button, energize it, basically close the switch, and then you keep tracing, and below there you have a dual trace, of that thing. And when the reflected wave comes back, you'll see it jump. So it went twice the distance to the fault. You know the velocity on the line, right? You can see the time between the reflected wave returning and the source wave leaving would be 2 times the round trip. You divide that distance by the speed of light on that media, and then divide by 2, and you've got the position, so you can drill a hole wherever that is, all right? It's just using this like you would echo returns. You know the speed of sound in a canyon? Takes that long. It actually took what? It went 2 times the distance to the reflected wall. You divide that by the speed of sound, you got the distance. It's used, I mean, this kind of stuff's used all the time in electromagnetics. It's used for a lot of things, but we have to make sure we understand the bounce diagram to do a lot of this stuff. So anyway, we get this. Now, we're going to get the voltage first at the center line, and I'll use blue for this one. So the only thing we're going to do up here is actually show this. This is going to be, this is at 0, this is going to be time, this is TL, this is 2TL, 3TL, and 4TL. Now 4TL is really 2 nanoseconds, right? Follow me, class? So if you look at this, just take a look. We're right at the center. At t equals 0, nothing on the line. Everybody agree with that? Keep going. When does this occur?
At 0.25?
Exactly half
Seconds.
the TL, right? TL
half
over
TL.
2, or 0.5 over 2, or 0.25. So I'm just going to put TL over 2. So it's TL over 2, which is exactly equal to 0.25 nanoseconds. So it goes from 0, it goes to V prime, which is 6.25 volts. Do you agree with that? Everybody? How long does it stay there? Until what? This guy comes back, which is exactly what? TL, right? Isn't that right? So that means that I come out to 1.5 TL, which is here. That stays there, but I add the next value. So the reflection coefficient at the load is 1/2, right? So I'm going to take 1/2 times V prime, and V prime is 6.25, so it's really going to be what? 6.25 times 3/2, isn't it? It's going to go up. It's going to go to 6.25 times 3/2, or 1 plus 1.5, and what is that? That's, oh my gosh, I don't know, 8 something, is that right?
Do it now.
Huh?
Do it now.
And you can look at the solutions.
It's 9.3. You said times 3/2, right? Yeah, it's 9.375.
And I assume the solutions bear that out? Anybody looking at it? This is for the voltage halfway. No. 9.375?
It's like halfway up.
Huh?
On the graph, it looks like 9.5, but it's
Don't worry about it.
Yeah.
If he doesn't, that's what it's going to look like, all right? It's going to stay at that value for how long? Well, hold it. Here's where it transitions to that right here. What? This is where it goes. So this is going to be 9. Did you say 3.5?
Yeah, sure.
All right, it's going to stay there for how long?
Till there.
Until I hit 2.5 TL, right? Exactly a full time constant. And then what does it do? It goes to, now, look, hit here, right? I have this thing coming down. Now I've got to add this to it when it hits this point. Do you agree with this, class?
Yeah.
All right, what's this thing? So it's V prime gamma L. So it's V prime, which is 6.25 times 1/2, right, times minus 1/4. So this is actually going to subtract something from it. So right here, what are we going to have? It's going to be 9.35 minus all that stuff, minus V prime, gamma L, gamma S, and what does it go to?
That's about 8.6 is what I got.
8.6, okay. Y'all with me on this, guys?
Oh, do you just for these values, do you just take your previous one and then add on or subtract
Yeah,
on
whatever it
you
was
fix.
here. Now, this is important to follow me.
Yeah.
Just remember that switch never unclosed, it's been closed. And because of that, the only thing you're doing is adding this component, plus this component, plus this component. Whatever was there, you add the next thing to
Okay, you
it.
just keep adding them as you go down.
That's right.
Okay.
And so down here, what happens, they want it to 4, right? So at 3.5, what happens right here? 3.5 TL. That's actually what? 3? So it's 1. Yeah, go ahead. What is it? So what does it do?
It's gonna be 6.25.
I got 8.2.
Now you're going to add this, right? You're going to have V prime gamma S gamma L squared, correct? Gamma L is 1/2, so it's 1/4 times minus 1/4 is minus 1/16 times V prime. You agree with this, class? So it's going to go down again to what?
8.6 minus.
What? 8 point?
8.2,
Yeah, 8.2.
All right.
and then it ends.
Now, I'm going to tell you, one thing you're noticing is that the jumps, the amount of jump is getting steadily lower. You all follow me? It's asymptotically approaching no jumps. But here's the thing, for that transmission line, if you let this thing just, the time go out to infinity, it's a very important point I'm about to make, because that source voltage never changes, it's there. What happens is, the actual line will look like just this, RS, whatever the voltage is here, VS, and then you can forget that transmission line. Now it's just 2 conducting pieces of copper. Here's your load, right? Whatever he calls it, I call it R load. And the voltage on the load is the voltage anywhere on the transmission line. Because now the transmission line just looks like 2 pieces of wire. Nothing's changing as time goes to infinity. You all follow me? And that voltage right here, as time goes to infinity, will be VS right here. And it's going to be times, I'll call it RL. RL over RL plus RS. In our case, this right here, the VS was 10, right?
Yep.
RL was it 100?
150.
150 over 150 plus 50.
It's 30.
What?
The source voltage, the source resistance is 30.
Oh, I'm sorry. My bad. Sorry. What is
8.3333.
3 volts? And you can see how the last jump is getting closer and closer to that. That's where it's going to asymptotically approach. Y'all with me? Now that's how you kind of keep your heads on straight with these things. If you think you got something wacky, think of the way it should go. It should be asymptotically approaching that.
And it'll pretty much approach that in like
Couple
way
more.
less than a second. So
Oh gosh.
like basically instantaneously.
Yeah. So now that's at the middle, right?
Yep.
Let's do it at the load, then the source. You all with me, class? Leave that up there. I'll put it here.
So it's
Okay. So if we're at the load next,
So what we just did was at the source. That was
No, that was the middle.
that was
Middle.
That was the middle. Oh, because we did that halfway.
Because we drew the thing straight down the middle.
Oh, so source load and middle. It's based off the bounce diagram.
yep, absolutely. You go to the
Gotcha.
bounce diagram.
Okay.
Okay?
Yep.
I come over here. This is for the load. Now, come down here, you gotta draw these things. Engineering paper is probably very useful here with a crosshatch paper. You guys, you've got it here. It's useful. I think they have this light green crosshatch stuff you can use too, but any kind of engineering paper that's got some way of easily doing this. So for the load voltage at the load, here's 0. Now, it's 0 until what?
Until it hits the load.
Gamma L. I mean, tau L, right? The time delay, which is
TL.
exactly half an answer.
Yeah.
I'm getting that. I like to think in terms of TL. I know that TL here is 0.5 nanoseconds, but I put it down here. And it's going to stay there. Matter of fact, the nice thing about being at the load is all these things are integer values. And he wants us to go to 2 nanoseconds, so that's 4 TL. Okay? Now, nothing until you hit here. But when you hit here, this is important. This is missed by some students. This is the superposition of the incoming and outgoing wave at that point. You see? So it's going to be 1 plus gamma L times V prime. So it goes to a value here of 1 plus gamma L V prime. The actual value is going to be what? It's 1 plus 1/2 or 3/2, right, of V prime, which is 6.25, and 8 point, what is that? Somebody just give that to me.
9.375.
3/2?
3/2 times 6.25.
9 points.
Yeah, it's 9.3.
9.375.
Okay, 375, I should know that. It stays there for how long, class?
Until 3 TL.
Right? Takes 1 time constant to go back, 1 time constant to come back down, right?
Yep.
I want to make sure I get everybody's attention. Y'all with me, class? Now, here's the next transition point, right? That stuff that was on there stays there. But now you're going to add this incoming wave, which is gamma L gamma S V prime, plus this outgoing wave, which is V prime gamma S gamma L. Y'all hear me? So here, you're going to have to add that. And I don't know what that is, but I think the transition is down. I'm not certain.
Yeah, it is.
And that's going to be, this is going to be 9.375 plus, and then I can put V prime here, 6.25. And now it's going to be gamma L, gamma S, so that's minus, what is that, 1/8, and then it's going to be gamma L squared, or 1/4 times gamma S, so it's going to be what? That's 1/4 minus 1/16, is that right? Tell me what that is.
8.2.
Is that what you, 8.2? Is that right? Might be.
Oh, wait. Oh, mine's done it wrong.
Y'all know what I'm doing.
Mm-hmm.
I'm just taking this value, whatever it is, and this value, and I'm adding it to the prior value. Y'all with me? All right, what do you get?
8.2. Yeah, no, I did it again.
This is 8.2? Okay. What's the book say? I think it's
It's like, yeah, it's like 7.5.
Wait a second.
Really?
Then we didn't do something right. Okay, so it's 9.375 here, right? Now go ahead and do this. So we're going to take this and this. They're both negative. So I take V prime, which is 6.25. This is how much you're going to subtract off. I have gamma L, which is 1/2, right? Gamma S is minus 1/4, so it's minus 1/8. Correct, class?
Mm-hmm.
Minus 1/8, and it's going to be minus, then I have gamma, gamma L squared, that's 1/4 times gamma S is minus 1/16, right? So that's going to be what? Minus 6.25, and here we're going to have, that's minus 3/16. Take that value, whatever it is, and add it to 9.375. Tell me what you get.
Still 8.
8.2.
It could just be his scale.
8.2.
He separates it by increments of 5.
Okay, that's the answer. I don't know what his graph is.
Yeah, you can. The dotted line right here, so it separates it by 10.
Oh God, you can't tell that.
Yeah.
He drew that with MATLAB. He didn't put enough demarcations in there, enough points. Y'all with me on that, class? And how far? That is to the end, right?
Yeah.
And he wants it at the source, right?
Yep.
Oh.
Yeah, he wants the source too.
Okay, at the source, what happens? We'll do it here. Well, When does the first transition take place?
It doesn't, does it start at V prime?
Here's T, this is 0, right? Switch closes at 0, right? You're at the source. It starts right at 0, doesn't it?
Yep.
So what's the value?
V prime.
V prime. That's exactly it. It starts with V prime. How long does it stay there since we're...
Until 2T?
That's right. So this is V prime, or 6.25. Now at 2TL, what happens? Now be careful, because just like the load, what happens? Now you got to add this incoming, right, which is V prime gamma L, and this outgoing, which is V prime gamma L gamma S. Correct, class? You with me on that?
You have to add both of them.
You have to, because here's the load, right?
Mm-hmm.
So at this point, one's incoming, one's outgoing at the same time. You got to add them both.
Okay.
Y'all with me?
Yeah.
Did you follow me on this? Okay. What do you get for that?
8.6.
Is that 8.6? Guys? Okay. 8.6. How long does it stay there?
Until 2 nanoseconds for TL.
4 TL, and then what happens? You take that value, right? And what do you add to it?
The two of those.
V prime gamma S gamma L squared plus V prime gamma S squared gamma L, correct? It's probably going to go up a little bit, I don't know.
Did you get 8.1? What'd you get?
8.3? Is that what you got?
Yeah, I got 8.6. Wait, are we supposed to do what did you supposed to do?
Here's another way to do it.
So 8.6 is the sum of these three, and then 8.3 is the sum of these four. I mean 5 on 5.
If you look here, here's another way to look. Here, we're at the load, right? If we want to know what the value of voltage is at the load at any point in time, this is on the transmission line, it's V prime here. At this point, which is 2TL, you have to add the incoming and outgoing wave. Then you have to add V prime TL plus gamma S to that V prime. Then down here, you're going to have to add V prime gamma S gamma L squared plus V prime gamma S squared gamma L squared to what was here.
So it'd be the sum of all 5 of them.
Yeah.
Yeah.
That's right. And it keeps summing up. There's all sorts of ways to write this mathematically, but seeing it is the easy way. And I don't know, where does it go to again?
It has a decrease, right?
I think it's going to decrease by, I can't tell you by how
I got 8.3. I don't know what you got.
I haven't got it.
8.3?
Yeah.
It sounds about right. And where's it asymptotically going to go to?
8.333. That number.
What was the value of the voltage we calculated when we did voltage division?
It's 25 thirds. It's 8.333.
Okay, that's where it's going to go to after all the banging is done, after the time goes on forever. Y'all with me? So that's a standard bounce diagram. Now, I'm going to show you a couple of things that happen that, now this is just for a switch that closes but doesn't open. And you should be aware of when you have a waveform that's a transient waveform. Let me show you what I mean. What's the weather supposed to be like here
Today or tomorrow?
today? If you don't mind.
It says or like not partly cloudy.
Yeah, 30% chance of rain from 5 to 7 plus.
Yeah, yesterday I looked at WeatherBug before I went up to the gym to work out.
Oh yeah, it started pouring.
WeatherBug said 0% chance of rain in the afternoon. Does anybody else look at these things?
Yeah, it started pouring out of nowhere yesterday.
So I'm driving in to go work out, and I get ding on the phone. It's a lightning alert. Lightning within 12 miles. Before I get there, it's like ding again. Lightning within 10 miles. 0% chance lightning. Something is not consistent. Get in there and I start working out. Literally 15, 20 minutes into my workout. It was raining like you wouldn't believe. It was like a hurricane kind of rain. It was just going crazy. I mean, these weather guys got to get on the stick. Now, maybe AccuWeather and Weather.com had it right. I use Weather Underground a lot. I found out that they're more, I'd say, precise in this area. than some of the others. Do you know what I'm talking about when I say these? Does anybody know what weather underground is? All right, if you look it up, there's a ton of weather apps, but this one will give you everything. The lightning location fields, give you everything, and they're pretty good. They're the ones that warn you before. So listen to that. So now we're going to do this kind of thing. What if we have this kind of a waveform we have as the input, where it's a pulse. It comes on and turns off. We'll call this V naught. Turns off at some tau. And this is going to be the voltage of the source. Right? So this is Vs of t. Y'all follow? So if we got that, think about how you would model this mathematically. Doesn't Vs of t look like just V naught U of t, or V naught U of t, that turns on to equals 0, right? Minus V naught U of t minus tau. Y'all follow me? So some of you probably have already thought this through. What I can do is do a bounce diagram for just this, where the switch closes at t equals 0. Do y'all follow me? Use this as the source voltage and do the bang, 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 bang. And then time delay a voltage by that much and have the value of the bounce be negative. Do y'all follow me? So I'm going to just show you what the circuit looks like. Now this is one of the problems. Look in your book. There's so many different facets.
This is repeat with a pulse of 0.4 nanoseconds.
Yeah, for a 10-volt pulse.
And that's the one you gave us, is 2.4 volt.
This is a good one. Because it forces, when you don't, I give you solutions. So if you struggle with it and you're wondering, you can look. Usually a question answered when it first occurs to you, it stays with you the longest. I was told that by a psychology professor when I was in school. He didn't give me a reference, but I'll trust him on that one. So for this one, first I have to draw a circuit. Here's a circuit I'm going to use. This is where my waveform is, like here, where it's V naught or 10 volts. Then there's some source resistance, Rs, and was it 30 ohms last time?
Yep.
Then here's the switch, but, right, for this, what we're going to do is this. First, we're going to get this bounce diagram for just this being a voltage source of plus to minus V naught. And here comes my transmission line. I have a characteristic impedance Z naught, which is 50, right? And then I have my load here, which is, was it 150? Yep, 150. Got a link down. And the velocity on this is,
Two-thirds the speed of light.
tell you what, we'll just use TL because it's the same, all right? TL for this one is half a nanosecond, right? Correct, class? Remember, it's the same as before. So now, come down here when you do a bounce diagram this way. I'm going to use the black one for this. So it looks like this. This is just for this one. This is going to be 0 TL, 2 TL, 3 TL, 4 TL, and 5 TL right here. And this is the load. And this is the source. And now I do a little bounce thing. This is going to be for this one. Just like before. Here, this is just V prime. This is V prime gamma load. This is V prime gamma load. gamma source, this is V prime, gamma load, gamma source, gamma load squared, gamma source, and this is V prime, gamma load squared, gamma source squared, and this is, go with me? So now, we're going to go, let's do this one at the center, but I'm going to show you right on top of this. Remember, that's the positive going waveform. And right behind it, we have this. Now that's positive, right? Now we're going to do the bounce diagram for this. Just hear me. And do it. In order, remember, this is the next bounce diagram. So over here, I'm going to have a waveform that's going to have a value of minus V naught, or it's going to be like this. This is going to be minus V naught, or minus 10 volts. Everything else is the same except for one thing. This switch closes at t equal tau, whatever the time delay. What was the time delay? Quarter nanosecond or something?
It was 0.4 nanoseconds.
All right, so the time delay is 0.4 nanoseconds. Now, he chose that for a reason, because it's going to irritate you. All right, so now, TL is what? It's actually 0.5 nanoseconds, correct?
Mm-hmm.
You all with me? Now look, when does this thing start? It starts at just before the first time constant occurs, right? So it starts right here. And this is going to be my minus V prime. Whatever V prime is, this becomes minus V prime. Can you all see the ration?
So that's at 0.4 nanoseconds?
Yeah.
Okay.
Right here. This is going to start at 0.4 nanoseconds. Now follow me on this. The only thing we're going to do is take this whole thing, shift it down, right? This is exactly what I've drawn there. Shift it down and make it negative. You'll see. And it should make perfect sense. So now we're going to have this kind of thing occurring. Up here. So it's going to go. And this is going to be minus V prime. Then from here, right here, this is going to be, I hope you can see what I'm doing. This is going to be minus V prime times gamma load. It's here, it's coming back. You can all see what I'm doing, right? This is going to be minus V prime gamma load, gamma source, and it's coming this way. But we keep on going this way. Y'all follow me on this class? So I took the exact same thing, only now these are negative values. Y'all follow me? I want you to make sure you see this. And it should make sense to you. We're just going to, in order to realize this right here, we're first going to get the bounce diagram for just the positive going waveform. And then add to it the bounce diagram of a negative going waveform time delayed by that. You all with me? You see the rationale behind it? You good on this?
Yeah.
All right. I want to do it over here. I want to make sure you see this. So let's do it right at the center. That'll be clear, but it'll be clear any place. So if we look right at the center, and look, this is versus T, and this would be TL over 2. Here's TL. 3 halves TL. 2 TL. 2.5 TL. And 3 TL. 3.5 TL. And finally 4 TL. I'm just trying to show you that they're not exactly drawn to scale. So nothing, take a look at this. Nothing occurs until V prime crosses this point. You all see this? You're going right down the center here. And you see you come to that point. I want to make sure everybody, you see that? What do? You add V prime. So at TL, it goes to V prime, right here. So it comes up, and just put it as V prime. Now,
Wouldn't it be have to, or is you wrote it?
Okay.
Yeah, you got it.
it's TL over 2, so it's what? 0.1, or 0.25 nanoseconds. I'm just showing you, I always think in terms of TL. Okay, that happens. Now what happens? Well, nothing happens until right here, right? And at that point, what happens?
So you just go back down to 0.
Now, it becomes minus V prime plus that, right? It goes to 0. Do you all see that? V prime and minus V prime, same magnitude, opposite sign, correct? You agree with this? Just think, this should make sense to you, right? Guys?
Yeah, it makes sense.
All right,
Yeah,
so
yeah, it makes sense.
it goes to 0.
I wish I lined it up better, like.
All right, so that's right, now where is that?
So that one right before, like,
Right about here, right? I'm sorry, my bad. This is,
It goes to 0 at 3 TL over 2.
well, this is TL over 2. Now, that's going to be 0.25, right? Add 0.4 to that, because that's the width of the pulse, right? 0.4? You agree with me? So that's a what? 0.6, or you're going to add this. It takes half a second to get down. So halfway there would be 0.5 over 2, right? My bad. That's in nanoseconds. Now, to that, to find the next point where it changes, it would be 0.4 over 2, or you're going to take 0.25 nanoseconds plus and 0.2 nanoseconds. That's 0.45 nanoseconds. With me? So, maybe I should put this. So it's just before here. So it goes up. Wait a second. This is going to be actually 0.5 nanoseconds, and this goes down at 0.25. Right? So that's right 0.045 right here, like so. This is going to have a width of tau. You can see what happens. Do you agree with that, class? Now, in his answer manual, he's going to, I think, graph this, if you look there.
That's the width of cow, where cow is.
Point what? It's 0.4 divided by 2 because we're only going halfway down.
Okay.
But wait a second. Wait,
He has it dropping after point.
hold it. It does. My
it
bad.
needs to go another one.
I gotta increase the spacing so you can see. We'll do it this way. This way we won't mess up. Come down here. This is going to be exactly TL over 2, and that's going to be exactly 0.25 nanoseconds. I'm going to do it this way. All right. So it's going to stay at V prime here. It's going to start here, then it goes to V prime right there. Now, the next transitional point is right here. And that's going to occur at 0.25 plus 0.4, because that's the delay time. So that's going to occur over here. I'm sorry about that. 0.65 nanoseconds. You're right. And there, it's going to go to 0. Y'all agree with this? And this would be 6.25 would be the magnitude. Now, I'm here, right? You can almost kind of get an idea what's going to happen. It's going to come down here. The next, what? The next is going to be this, right? Now you're going to just add this value. The other, there's nothing left on the line. So now it's V prime gamma L gamma S. So it's 6.25. What is it? I'm sorry. It's this point. I drew this thing terribly. So now it's going to go to, this is going to be V prime gamma L right there. You see it's going to be delayed by, this is going to occur at TL, and, I'm sorry, at 1.5 TL, so 7.5 nanoseconds, 0.75 nanoseconds. I'm going to just call this 0.75 nanoseconds. See, this pulse, this came, that's the black one. This is the blue one you subtract. Right below that one, right? There's the black one, and that occurs at 1.5 TL, or it's exactly 7.75 nanoseconds. Do you agree with this, class?
Yes.
And then you're going to add just gamma L, which is 1/2 times 6.25, so that's 3.125. So that's going to go right here to 3.125 volts. Do you see that? And look at the answers, the solutions. When you look at this, he has this kind of thing occurring, right? You all see the progression? How long is it going to be there?
For 0.4.
Well, it's going to, if you take a look, that happened, right? Keep coming down. There's a delay of what? 0.4, right? And then it's going to go to 0 again, right? But you can keep, can you all do that, class? Do you follow me on this? You're basically superimposing a positive going pulse, then you take a time delay with a negative, do the same trace. If you have engineering paper, this is easy. It's hard for me sometimes to scale things on the board. And just take a straight line and go down. Now, what happens at the load? Just to talk about for a second. Well, at the load, nothing would happen until the first time constant. Do you agree? And then what would happen? Well, it would be 1 plus V prime, 1 plus gamma load times V prime would be the value. Agreed? Now, exactly 0.4 nanoseconds later, there's going to be a superposition of this and this at that point. And it's going to be subtractive, right? It goes to 0. That's exactly what happens there. And then you keep going down, and basically you just, every time you hit either a positive or negative going thing, you add them. I use 2 different colors to try to show you. If it's blue, it's subtracted. If it's black, it's additive. Does this make sense to everyone?
Yeah.
Good. Okay.
Was the 0.4 nanoseconds given, or did
Yeah.
you add it was?
In the problem statement, he says the pulse has a duration of 0.4 nanoseconds. But that's how you do it. By the way, asymptotically, what's the value going to be on this line as t goes to infinity? Anyway, what's the value of voltage at the source as t goes to infinity? It's 0, right? This is, after this tau, the voltage is gone. Y'all follow me on that? So if the voltage is turned off at the source, then that means the value anywhere in the line as time goes to infinity will be 0. That's all. So if you have a transient pulse, it'll always go to 0. Okay? All right. Now, there are other problems in this book, in that section. Stu has stuff with inductors as determination and capacitors. I'm not going to do that part right now. If we have time at the end of the semester, I'll do it. It's pretty straightforward because the only thing you're going to do now, how did you calculate, remember the RC circuits or RL circuits where you had transients back in the day? You had Dave Irwin circuit classes. Do you all remember that? What would happen? Well, you'd always have, if it was a capacitor, charged at a rate of what? It would be V naught, it would be 1 minus e to the minus t over tau, right? That would be the value of the voltage as time progressed to charge a capacitor. And for an inductor, the voltage would die off as that, right? It would be V naught, whatever the V load, would be e to the minus t over tau load, and tau would be, for a capacitor, tau is RC. For an inductor, it's L over R. But I don't want to go there yet because this could get it's a little too confusing and not that beneficial. We're done with chapter 2. We're going to chapter 3 now. Okay? So in chapter 3, that's electrostatics. And you have had physics. A lot of this is second nature to you, or at least you've had enough so if you're an engineering student, usually you're real good at physics and math. That's, generally speaking, I don't know what your counselors tell you these days, but if you're real good at physics and math and you like that engineering is sort of a natural career for you, if you struggle with mathematics and physics, then engineering is not recommended because you're just going to get even worse. Engineering is more or less applied physics. And it gets more involved and more confusing if you don't have a real solid ground in physics. That's the reason they tell people, at least they recommend that if you don't really like nail physics and mathematics, calculus, differential equations, all that in physics, then you may not want to be an engineer. That's at least my version of what they'll tell you in a polite way. So here, we're going to take a look at chapter 3, and it's electrostatics. So what is electrostatics? It means nothing's changing with time. They take a ball of charge, they stick it there, it's there. Tell me what it does. So the first thing we always do, and this is like general physics, you start with, well, what happens if you have two pieces of charge? So in general, if I have charge 1, Q1, and I have another charge Q2, and they're separated by some distance R, then I can say the force on either charge in opposite directions, I'll call this F on charge Q2. The magnitude will be 1 over 4 pi epsilon naught. Here epsilon naught is equal to, Whitworth likes to do it this way, 1 over 36 pi times 10 to the minus 9, and it'd be farads per meter, and it's approximated as about 8.825, or actually 8.854, pardon me, times 10 to the minus 12 farads per meter. I tend to use this one more. And then it's times Q1 and times Q2, and it's divided by the distance squared. Now that's the general form of the magnitude of force. The direction of the force will always be such that like charges, if they're both the same polarity, both positive and both negative, will repel. I'm just giving you a very general sketch of it. Do y'all remember that? Like charges repel, opposites attract. Follow me on this, guys? Y'all remember this from physics? It's very obvious, and that's just the general form. Now, I'll tell you a trick. For this force equation, you can do something, and they may have done this in physics. They can use a constant K that's 9 times 10 to the 9, and then take that times Q1, Q2 over magnitude of R squared, and it'll give you the same answer. So do this for me just to see. If you take 1 over 4 pi times epsilon naught, tell me what you get. So you can do it. If you take 4 pi times that's, look at this. Just use this part right here. You have 1 over 4 pi, and then you have that, which is 1 over 36 pi times 10 to the minus 9. That's what? That's exactly 9 times 10 to the 9, isn't it? That's how they get that. In your book, you'll see this. In physics, I still remember this. I use this. Just put 9.9. 9 times 10 to the 9. You don't have to write 1 over 4 pi epsilon naught all the time. Y'all with me? Do you remember that from physics? It's a nice little trick. All right. Now, again, I've told you this just to let you know how to calculate the magnitude. In general, if you have any number of charges, Q1, Q2, doesn't matter how many, Q3, and you want to know the effects of all these on some charge Q4, you simply sum up the forces from each of them. So the force on Q4 would simply be the sum of the forces from really Qi to 4 added together, where I would be 1, 2, 3. In other words, you're just going to add them up vectorially, the forces. I think you get this. I'm not trying to be too precise about this, for the simple reason I think most of you understand this. You can add them up. Now this is all for just discrete charges. You add the forces caused by each charge on the charge that you want the force on. And the force is always proportional to the two charge values divided by R squared, and it's always in a direction that's pointing to the two charges if they're opposite, and away from the two charges if it's the same charge, either two negatives or two positives. Now I'm going to move, because this is not something that is very valuable in the general sense. From the physics perspective, this is how they actually figured out all this force business, the constants. They basically, a lot of things they did. They knew gravity before they did electromagnetic force as well. So if you have two charged balls, each of them with a given mass, and you tie a string, a dielectric string to it at a center point, they're going to repel, right? If they're the same charges on the ball. So the force would push them apart. They'd go like this, but gravity's pulling down. So then you make a simple force triangle. You know what the mass of those things are. You can pull the effects down, you can measure the angle, and from that you can do a force triangle. That's the string's tension, that's gravity, that's that. Sum of the forces has to be 0, and you can extract the value for a given charge of the constant K and vice versa. But there were measurements. All these things that we do, this is important, at least you hear it from me. I gotta say, all the things that we do in electromagnetics are based, the field equations, Maxwell's equations are based on measurement. They're not, Moses didn't come down from Mount Sinai, just here's the equations, there they are. No, they're based on measurements, lots of measurements and observation. The mathematics is precise in terms of its ability to describe it, but they're based on measurements, all those constants, including the speed of light, by the way. Even though Maxwell's equations, based on the assumption, a couple of assumptions, it did give you the precise value. Okay, next, we're talking about the electric field. That's something that you've got to be familiar with if you're in electrical computer engineering. And there's a lot of people that contributed. Gauss, Faraday, probably no bigger than James Clerk Maxwell. Yeah. Oh. So what I'm going to tell you now is when we deal with most stuff, the charge equations, those force equations, they fall out of this. You know how if you have two charges, I'm going to show you this, Q1, and you have some Q2, and there's a distance R between them. Then there's a force on Q2, call it F2, caused by the first one, and that force would be K Q1 Q2 over the distance R squared, and it's actually in a unit vector direction that would be, if you think about this, if R is a unit vector from this point to the point of observation of the force, I'm going to call that vector R. The unit vector AR I'm talking about is just vector R over magnitude of R. Now, a unit vector has a magnitude of 1, and it points in a given direction. All right, and we'll get to that. So that's really the force on 2, but we don't care that much about the force. We'd say, forget about the force on Q2. What if Q2 didn't exist? Then there would be an electric field component. What we talk about when we talk about electric fields, the electric field at any point is really the electromagnetic force. This is for electrostatics that occurs at that point divided by the charge at that point. So in our case, the electric field here from the first charge, and I'll draw it up here, if you have some Q1 and you want to know the electric field value at a point that has a vector R away from here, so this is a vector R, then the electric field would be K times the charge Q1 over R, magnitude of, actually R squared, magnitude of R squared, times the unit vector in the direction, AR. And AR would be R vector over magnitude of R vector. Y'all remember that from physics? I'm going to do examples so you get a good appreciation. This is R squared. Y'all remember that in physics? So, simple thing to do is just start with a single charge. If I have 1 microcoulomb at the origin, I'm going to put it at the origin. And I'm at a distance at a point right here that's going to be, say, x equals 2, y equals 2, z equals 2. This is going to be Cartesian coordinates, x comma y comma z. And I want to know what the electric field is out here. Can y'all follow me on what the problem is? I'm going to get this done before I make it quick. So how do you do that? Well, for this one, first, what is my vector R? My vector R, how do you always get a vector between 2 points? Take position of observation. I'm going to make this at the origin. This way it'll be easy to see. This charge is at the origin. You with me? So here, take position of observation, the x, y, and z coordinate, minus the coordinates of the position where the charge is that's causing it. In this case, R is just going to be 2ax plus 2ay plus 2az. I made it simple on purpose. Do you all see this? With me? Okay. Now, what about my electric field? By the way, what's the unit vector? I put down. AR is going to be equal to R vector over magnitude of R, right? We got our vector. It's 2ax plus 2ay plus 2az divided by the magnitude. How do you get the magnitude? If you have orthogonal coordinates?
Square all the
Square them all,
components
take
and
the
square
square root. So I have 2 squared plus 2 squared plus 2 squared square root. That's what? 2 square root of 3. You agree with that? So this is really going to be what? Just 1 over the square root of 3 here, and it's going to be times ax plus ay plus az. And that would be a unit vector AR, right? Now we get the electric field at that point. I made it simple on purpose. It's K, it's 9.9 times 10 to the 9th, right? Then it's times the charge, and I made the charge 1 microcoulomb. What's a microcoulomb, guys?
10 to the negative 6 coulombs.
That's right. So it's 10 to the minus 6, right? And then I have to divide this by R squared. Well, if you look at this, R squared would just be 2 squared plus 2 squared plus 2 squared, or 3 times 2 squared. Do you agree with that? So it's 3 times 2 squared, and then times the unit vector, which is 1 over the square root of 3, so this is going to have the square root of 3 down here. And then you would have just ax plus ay plus az. So if somebody could just give me this value, which is what? That's 9 times 10 to the minus, or 10 to the 3, so it's 9 times 10 to the 3. Divided by, and that's 4 times 3 is 12, so it's square root of 3 times 12, 12 and 9. It's going to be 3/4, so it's 3 over square root of 3 times 10 to the 3rd. And what's that value? 3 over square root of 3, 1.4 something times 10 to the 3rd. What is it?
433.0.
Say that again?
433.01 or something.
This is 433? Is that right? So 9 by 12,
That's right, yeah.
433? Okay. 433, and the units are volts per meter. Now I did try to make it as simple as possible. If you had any other charges there, you would add the electric field at that point caused by the other charges. I'm going to, on Wednesday, I'm going to go through some of this stuff in more detail and do problems. And I'm going to give you some reading and a homework assignment. Please do these things and come prepared. Here's why. In electrostatics, you had electrostatics that was very, I'd say, general stuff. I mean, you got voltage, you got all that, but the problems weren't complicated. These things get a little complicated, so please just do the homework. Y'all with me on this, everybody?
Yeah. What's the quiz going to be on Friday? Bounce diagrams or electrostatics or both?
It'll be, yeah, bounce diagrams. But, well, I think, wait, we got to see how much we cover Wednesday. It might have electrostatics already.
Okay.
Because this is only Monday.
This is what? Oh, only Monday.